Yes, so I'm very glad to be here in Dagstuhl for the nth time. Somehow I never get sick of it. It's always nice. So today I would like to speak about an embedding of the Baire space of all sequences into the natural numbers. See, this thing sometimes makes these lines, and then you have to do this, and then you have to repeat the exercise. So I think it is only fair to say that there is no such thing, right? So let's first prove that this is, oh my, okay, this goes away. I meant this, okay? So I would like to have an embedding of the Baire space into the natural numbers. So let's first prove that there is no such thing. So one way to prove this, say classically, I will review a proof that Paolo Oliva gave me yesterday. So suppose you are given a map from the Baire space into the natural numbers. So then the first exercise is that you find a j going in the other direction, satisfying, let me get this right, I j of I applied to any f has to be the same thing as I applied to f. This is very easy to do once you actually try to do it. It requires a little bit of excluded middle and a little bit of countable choice. But anyway, you can get such a j, and once you have the j, you say, let us consider n, which is the I applied to diagonalization, which is then lambda k j k k plus 1, okay? And define f to be the map Jn and G to be this map here. So G is lambda k j k k plus 1. And so then now we compute a little bit. So first of all, what is Fn? Fn is j and n, but this is certainly different from j and n plus 1, which equals g of n. And so therefore f and g are actually different. However, I of f equals, so now I use this thing here, I of f equals I of j of I of f, like that. Okay, I'm not going to bother with this one here. And so this now is supposed to be the same as I of g. And I'll let you contemplate on that. So what we have actually proved here is that given any map I from the Baire space to the natural numbers, we have actually produced a counterexample to injectivity, and Paolo Oliva has nice ways of extracting interesting programs from these. And so this is all very well, but if you're not a classical mathematician, then you may think, well, how about a constructive proof? Okay, so what would a constructive proof look like? So here's constructive proof with a little bit of continuity. So as soon as you have a little bit of continuity, then it's very easy to do the same thing. So for example, the following kind of weak sequential, I'll call this weak sequential continuity. It's the principle that says if you have any map, then it maps limit points to accumulation points. So if I have that the limit of some sequence xn is a point x, then when I apply a map to the sequence, I get a new sequence and this sequence has f of x. I could require that f of x is now the limit point of this sequence. That would be sequential continuity, but it actually suffices for this proof to require that this is an accumulation point. Okay? So then you repeat the argument. Now it actually, in my opinion, it gets simpler because you don't have to do these strange things with diagonals. So take any I from n to the n to n, and consider the following sequence. Now I'm going to take a sequence of functions. So I have fn of k. I want this to be a sequence which converges to the everywhere 0 function. So for example, I can say this is 1 if n is less than equal to k, and it's 0 otherwise. So fn is this sequence. It has a bunch of zeros and then it has ones, like that. So there are, I think, n zeros. And so the limit of fn's in the usual way, so you take some, you take the usual complete metric on n to the n, then the limit is going to be the everywhere 0 function. Hence, if I apply my I by this weak sequential continuity, then this sequence will accumulate around I of lambda k0. But since the metric on n is discrete, this means that there has to be at least one term. So there exists some k such that I of fk equals I of lambda k0. And we're done. Because fk is different from lambda k0 everywhere. So this is now a constructive proof, but we used a little bit of continuity. So we want to know, how about getting rid of the continuity? And a while ago there was a discussion on this on the constructive news mailing list. So I'm essentially reporting on what happened. Yeah, so you would want to have just Bishop-style proof of this fact. Especially since there is a constructive proof, and then there is a proof in Russian-style mathematics, in Bauerian, because they all satisfy this continuity principle. But it turns out you cannot have a constructive proof of this. So maybe then you say, okay, but this is a strong thing. Given I actually produce a counterexample to injectivity. So maybe I can just have a constructive proof of there is no injection. I try to weaken the statement. And it turns out that even that is impossible. And what I'm going to do is I'm going to show you a model in which there is an embedding of the Baire space into the natural numbers. So it is intuitionistically consistent to assume that n to the n is a subset of n. Note that it is not intuitionistically consistent to assume that there is a surjection from natural numbers to n to the n. That's a very easy diagonalization proof, shows you there can be no injection in the other direction. But there, as it turns out, there can be, no surjection in the other direction, but there can be an injection. Okay? Before I go on to the model, I would just like to stress one thing here. We are assuming that this I must be, of course, we are requiring it to be extensional. Okay? If you don't say that it has to be extensional, then I can just use Clini's number realisability and just my I would take a realizer for a total function and map it back to the same thing. And that would give me an injection, but it's not extensional. It does not preserve extensional equality. So that's not what I want. I want a real function here. So the thing that we're going to use is I will build a realisability model over infinite time Turing machines. Oh, the damn lines. Infinite time Turing machines. So these are Turing machines which were described by Joel Hamkins. And Joel and I are, actually I should state this, that Joel and I are thinking about these things together. We want to think a little bit about what kind of realisability comes out of this, but I think today I will just speak about this particular proof that in this realisability model you get an embedding of the Baire space into the natural numbers. So what are infinite time Turing machines? There is a very nice paper by Joel that you can read on this topic. So it's like an ordinary Turing machine. So an infinite time Turing machine is like a Turing machine, but it has infinite running time. So to make sense of this, we measure the running time as ordinal. So at each successor step, you do whatever the usual Turing machine does. You just perform the program. The question is what to do at limit stages. So what to do at limit stages. Let's imagine that we are at the stage omega. So this means the machine has been computing something for all the finite stages, and now we want to describe omega. Okay? So what we do is this. Also, by the way, I'm assuming that the cell tapes, the alphabet for the cell tapes consists of just zeros and ones. Okay, this is the easiest to describe. So you do the following. So you put the machine into the special limit state so that the machine will know that it has just passed through a limit stage. And you do something sensible with the heads, you know, like place heads in some fixed spot, like beginning of the tape. It doesn't really matter, because if the heads are just somewhere, when the machine wakes up and says, I just passed through a limit stage, it can always take all the heads to wherever it wants. It just uses up some finite amount of time to move the heads wherever it wants them. But it's better maybe to put them somewhere. And then the question is, what happens with the cells? So each cell is the lim sup of previous stages. So you compute the lim sup of every cell, which concretely this means the following, that a cell will be equal to 0 if in stages before alpha the cell stabilized at 0. And it will be 1 if it kept, if it was 1 from some place, or when there were cofinally many ones, if it had cofinally many stages below alpha with a 1. So it's just the lim sup in the usual sense. Okay, that's how it works at limit stages. So what can these sorts of machines do? Let's see. So what can they do? Well, one easy thing to do is decide the halting problem for ordinary Turing machines. How would you do that? Well, you get a Turing machine, T, and you simulate it for omega steps. And if the Turing machine ever stops, you write a 1 in a special cell. So after omega steps, you look to see what is in that cell. So if in that special cell there is a 1, that means the machine has stopped someplace, but if it is a 0, it never stopped. So you can tell that the machine stopped. Okay? So more generally, you can decide any sentence of piano arithmetic. So if you have some statement which has some nested quantifiers, and suppose there are k alterations, that will take you roughly omega to the k plus some change steps. Because simply what you do is, in order to decide, for example, let's look at how to decide for all, and then you have something here. Well, you just take your time. You try for every possible n. You just, you take the first n, you decide whether it's okay, recursively, so then this might already take infinitely many times. And then you take the next one, the next one, the next one, the next one, and you sort of keep your bookkeeping in these cells where you indicate a 0 if you found a counterexample, and so on. And so at limit stages, you're done. So you can decide statements of piano arithmetic. In fact, you can do much more. You can decide pi 1 1 statements. You can decide pi by 1 sets. So you can decide, in particular, you can tell whether a given infinite sequence encodes a well order. So that's pretty strong. Yes? But anything that you can decide is, it turns out, you cannot go beyond delta 1, 2. Okay? So you stay below delta 1, 2. For our purposes, we will need the following computational task. So, oh, by the way, maybe I should say this. So you can now think about type 1 Turing machines, infinite time Turing machines, and you can think about type 2 infinite time Turing machines, and you get a perfectly bizarre but nice, so you get a theory of infinite time computability, just like ordinary type 2 and ordinary type 1. So I'm now going to work with type 1, so which means that I have some encoding of machines. So given codes n and m of two machines, I want to not decide, but I want to semi-decide. So semi-decide whether the machines compute the same function from natural numbers to natural numbers. So I'm given a description of two such machines, and I want to have this tell whether they compute the same function. So I cannot really hope for this to be decidable, but I can hope for it to be semi-decidable. That is to say, I want to have a machine such that after accepting n and m, it halts if n and m compute the same function. For example, n could describe a partial function. So if n describes a partial function, I'm going to have a problem. Then my machine is allowed to diverge in such cases. Okay, so what we do is, so the first thing we do, you get the usual SMN and the UTM theorems and so on. So what I'm saying here, you can simulate machines and so on. So this works. So the first thing is you write down f of 0, f of 1, f of 2, and so on, the infinite sequence on the first tape. This takes an infinite amount of time, but if there is a special halting. There is a special halting state for these machines, and so if the machine ever enters a halting state, then it has halted. Otherwise, it hasn't. So it turns out that the running time of such a machine is always a countable ordinal. So if a machine runs for omega 1 steps, then you can prove that it has entered the exact same stage of computation twice, and it will repeat. But you explicitly have a halting state. So you say, I have now halted. You cannot halt on a limit ordinal, but you can halt on any successor ordinal in principle. It's a very interesting question. What ordinals can you halt on? So that's something that Joel, for example, discusses, and he calls them clockable ordinals. And not all countable ordinals are clockable, and so on. So it's a whole theory. So let's do this. Okay. So we write down whatever the first machine computes. I cannot say f here. So let's say that n describes some machine t, and m describes some machine s. So write down whatever t does on 0, on 1, on 2, on 3. First I simulate t0. When that halts after some infinite amount of time, then I simulate t1, then I simulate t2, and I write down all this stuff onto a tape. If, for example, t applied to some number doesn't halt, then my simulation will go on forever. But that's okay. I just need to decide I just need to semi-decide that in case of total machines. Okay. Then after that, we repeat the same thing, but with s. And we do this on tape 2. And then, once we have written down the two functions, so if we fail to write down the two functions, then that means one of them was partial, and it's okay, we diverge. And then just take omega steps to compare. To see whether there is a difference. Okay? So that's the sort of thing that an infinite time Turing machine can do. So we're now very close to embedding, and how are we going to embed? So let's take type 1 infinite time Turing machines and the realisability model over that. So it would be like Kleene number realisability, but with infinite time Turing machines. And I can do the following. I want to realize an I which goes from, I want to realize, go away, I from n to the n, and now this n to the n is inside the realisability model, yes, to n, and I want it to be injective. And the idea is that I'm just going to compute canonical realizers for total functions. So this I, what is a machine realizing I doing? It will get a realizer n, it'll get some realizer n which realizes some f in n to the n. So this is this n describes an infinite time Turing machine that computes a total function, okay? And so now I want to take this n and I want to output some number. So I cannot output n, that would not be extensional, but I want to compute a canonical k which realizes f. Okay? And the way to do that is I use the dovetailing technique. So in parallel, I run in parallel for each k in n, semi-decide that n and k realize the same function. So this is going to be some specific parallel search technique which simulates infinitely many semi-decision procedures that I just described. You know, one comparing n to 1, another one comparing n to 2, another one comparing n to 3. And one of them is going to, so by the way, this is not going, so I can arrange things so that this does not depend on n, because I first write down the function that n computes on a tape. And then my parallel search will only use what's written on the tape. So I will use extensional information about the function realized by n. I will never look at n in my dovetailing. So I will just look at the tape, which already contains all the values. And so I go with, for k equals 1, I write everything down for k equals 1. If I have, once I see that everything has been written down, which I can test in infinite time, then I go, I compare. So this procedure will find one of the k's, but which one it finds does not depend on n. It only depends on what's the extensional information that n is holding. So if it ever finds a k, it will always find the same one depending on the extensional information, and it will find at least one k, or there will be a k that it finds, because if for no other, it's going to find n. N would work, okay? So this is going to give me a canonical representative. So we have to make sure that we don't actually use n in the dovetailing, but we have to use just the tape which describes what n computes. And so this is going to be canonical, and it will realize a function from n to the n to n, and it's obviously going to be injective, because if n and n prime compute the same f, that procedure is going to find the same k. So in this model, that's type 1 infinite time Turing machines, there is an embedding of n to the n into n. Okay? So I want to finish by saying something about why you would want to think about infinite time Turing machines. I mean, after all, this is it sounds like a very perverse subject, yes? You could go jumping up and down and say, no, but this is not really computable. So the first reason, which I think is the most important one, is that you want to be ready. When it comes, they're going to make this, right? So GR stands for general relativity, and the 2 dots means it uses 2 black holes, okay? So it can go up to omega squared, yeah? Yes? And you want to be ready, yes? You say, give me the computer. Just like Turing, right? He was ready. Before they made the actual computers, he was ready. He knew what to compute. Okay, so you want to be ready. But also, maybe more mathematically, you want to, I think it's a very good source of counterexamples. In constructive mathematics. And just because of this, I think this model deserves to be looked at. Also, notice that continuity is shattered by this model. You can very easily define very wildly discontinuous maps. However, there are descriptive set theory-like things. For example, the graph of every computable map is a delta 1-2 set. So I think there's a nice, maybe a somewhat unusual, but nice task here for a constructive mathematician, which is to figure out what replaces the usual continuity statements and continuity principles in Breuerian mathematics. In this case, it's going to be some non-classical principles, where they're almost classical, but they will actually be non-classical principles that have a flavor of descriptive set theory. So this might be a nice way of marrying descriptive set theory and constructive mathematics. Thank you.
Right, question. I was curious if you think if you had a bit less like just